Alright, let's go. Number 10. The Pioneer Anomaly. John Anderson was a navigation engineer at NASA's Jet Propulsion Laboratory, and his job in the 1980s was mundane by design. Track the radio signals bouncing back from the Pioneer 10 and Pioneer 11 probes, and confirm they were coasting exactly where Newtonian mechanics and general relativity said they should be. Standard orbital dynamics predicted a clean, predictable deceleration as the spacecraft climbed out of the sun's gravity well, nothing more than what the models already accounted for. Instead, both probes were arriving late. Every year they fell a little further behind schedule, as if something invisible kept tugging them back toward the sun. Anderson, along with Philip Laying, Eunice Lau, Anthony Liu, Michael Nieto, and Slava Turyshev, published the full analysis in a 2002 paper in Physical Review D, measuring a constant sunward acceleration of 8.74 times 10 to the negative 10 meters per second squared, present from roughly 20 to 70 astronomical units out, and unaccounted for by any modeled force. The failure parade began immediately. Fuel leaks were ruled out. Solar radiation pressure was too weak at that distance. Interaction with the Kuiper Belt's dust was calculated and dismissed. For nearly a decade, the anomaly resisted explanation, prompting serious proposals involving modified gravity and even dark matter clumped unusually close to the solar system. It took until 2012, when Turyshev's team, publishing in Physical Review Letters, modeled the thermal recoil from the plutonium power generators and the spacecraft's own directional heat radiation, to close the case as a mundane thermal push rather than new physics. But for over 20 years, two of the best tracked objects humanity has ever built quietly disobeyed the model. If a heat leak from an aging generator can counterfeit new physics for 2 decades, how many other anomalies sitting in some database right now are actually the same kind of ghost, still unexamined? The Pioneer Anomaly got its explanation. The next one on this list still hasn't. Number 9. The Spacecraft Flyby Anomaly. Engineers tracking Earth gravity assist maneuvers were simply trying to confirm that spacecraft exited their planetary flybys with the exact velocity predicted by classical orbital mechanics, a routine check performed on nearly every deep space mission. The physics here is airtight, and has been for centuries. A flyby should conserve orbital energy in the planet's reference frame, entering and leaving with no net gain in speed. In 1990, the Galileo spacecraft came out of its Earth flyby measurably faster than it should have. Then it happened again. And again. John Anderson, James Campbell, Eunice Ekelund, John Ellis, and James Jordan documented 6 such flybys in a 2008 paper in Physical Review Letters, covering Galileo, Near, Cassini, Rosetta, and Messenger, with anomalous velocity boosts ranging from under a millimeter per second up to 13.46 millimeters per second for the Near spacecraft's 1998 Flyby. Every proposed culprit failed. Atmospheric drag couldn't explain flybys at altitudes with no meaningful atmosphere. Solar radiation pressure was too small by orders of magnitude. General relativity's frame-dragging effect from Earth's rotation was calculated and found insufficient. Even an empirical formula built from the 6 data points, fitting latitude angles to the anomaly's size, could predict the pattern without explaining its cause. Some later flybys showed no anomaly at all, deepening the mystery rather than resolving it. The Rosetta team even used the formula to predict a near-zero anomaly for a subsequent flyby, and got it right, which almost made things worse. The pattern behaves consistently, yet nobody can say why it exists. Every satellite currently threading a gravity assist past this planet is being nudged by a force with no name. Nobody has closed this file. The next one measures the very thing gravity is supposed to be. Number 8. Conflicting measurements of big G metrologists at labs including NIST, the University of Washington, the BIM in France, and Hwazong University of Science and Technology were attempting something that sounds almost trivial: pin down the exact strength of Newton's gravitational constant, the number underpinning every calculation of planetary orbits, black hole masses, and cosmic expansion. Physics assumes g is a fixed, universal number, and every other measured constant in nature, from the charge of the electron to the speed of light, agrees with itself to remarkable precision across independent labs. G does not. Torsion balance experiments, Cavendish-style beam setups, and atom interferometers, all measuring the same constant, kept returning values that didn't overlap even within their stated margins of error. The 2018 CODATA report, compiled from 16 precision measurements, disclosed relative disagreement on the order of parts in 10,000, and one especially precise 2013 BIMRA measurement by Terry Quinn's team landed 241 parts per million above the accepted standard. A gap far larger than the experiment's own claimed uncertainty allowed. The failure parade here is unusually humbling. Nobody has found an error. Systematic bias in torsion fibers was checked and reduced. Thermal drift was controlled for. Different experimental designs, immune to each other's flaws, still disagree. Stacy Schlamminger's working group at NIST convened conferences specifically to hunt for a shared mistake and came away without one. Every structural calculation, every satellite orbit, every estimate of a distant galaxy's mass runs through a constant that laboratories on Earth cannot agree on. If we can't nail down gravity's strength between two rooms in the same building, what does that say about gravity's strength across a galaxy? We can't agree on how strong gravity is. The next entry proves it's stronger than anyone expected. Number 7. The oversized black holes of GW150914. The LIGO scientific collaboration spent decades building detectors whose original purpose was simply to confirm that gravitational waves, predicted by Einstein in 1916, existed at all. A checkbox experiment meant to validate a 100-year-old equation. Standard stellar evolution models predicted that black holes formed from collapsing stars should mostly fall in a modest range, rarely exceeding roughly 20 solar masses, since heavier progenitor stars blow off too much material before collapse. On September 14, 2015, the twin LIGO detectors in Hanford and Livingston picked up a chirp signal that didn't fit that range at all. The LIGO and Virgo collaborations, publishing in Physical Review Letters in 2016, calculated the merging pair at 36 and 29 solar masses, colliding into a single 62 solar mass black hole and radiating roughly 3 solar masses directly into spacetime as gravitational waves, an event brighter. For a fraction of a second, than every star in the observable universe combined. Astrophysicists scrambled through explanations. Could these be primordial black holes formed in the early universe rather than dead stars? The math didn't rule it out, but didn't confirm it either. Could low metallicity stars in the early cosmos collapse into unusually heavy remnants? Possibly, but the rate of such mergers detected since has kept surprising modelers. Could dynamical capture in dense star clusters explain pairing black holes this large? Still debated. 6 years after that first detection, LIGO and Virgo had logged black holes even larger, some pushing past 80 solar masses, sitting inside a theoretical mass gap astrophysicists had argued shouldn't exist at all. Somewhere out past the reach of our telescopes, the universe is quietly building objects heavier than physics says it's allowed to. The mass gap is still open, so is the question of who's watching those stars die. Number 6. The galaxy rotation curve mismatch. In 1965, astronomer Vera Rubin joined the Carnegie Institution's Department of Terrestrial Magnetism and began working with instrument maker Kent Ford, whose new spectrograph could measure the velocities of glowing gas at the edges of distant galaxies. A technical upgrade meant simply to sharpen existing observations of galactic structure. Basic orbital mechanics predicts that stars farther from a galaxy's center, orbiting less mass, should move slower, the same way Neptune crawls compared to Mercury. Rubin and Ford pointed their spectrograph at the Andromeda Galaxy and found the opposite. Stars at the outer edge were moving just as fast as stars near the core. Publishing in the Astrophysical Journal in 1970, Rubin and Ford measured Andromeda's rotation curve across 67 emission regions and found velocities that stayed essentially flat past 24 kiloparsecs from the center, with a mass-to-light ratio in the outer disk running 15 to 20 times higher than in regions like our own sun's neighborhood. By 1980, Rubin, Ford, and Norbert Thonard had confirmed the same flat curve in 21 more spiral galaxies. The failure parade started with the obvious candidates. Undetected dim stars were proposed and found insufficient to account for the missing mass. Errors in the visible light measurements were checked and ruled out. Modified gravity was floated and remains contested to this day. The dominant explanation that survived dark matter has never been directly detected in any laboratory on Earth, despite decades of dedicated search. Every galaxy in the night sky is apparently wrapped in several times its own visible mass in something we cannot see, cannot touch, and can only infer from the fact that stars refuse to slow down the way they should. Rubin found the shadow. She never found what's casting it. Number 5. Dark matter as gravity's missing math. Cosmologists in the decades following Rubin's discovery were trying to close a straightforward bookkeeping problem, account for all the gravitational pull observed across galaxies and galaxy clusters, using only the matter that could actually be seen through telescopes. Standard physics assumes that visible, ordinary matter, the atoms making up stars, planets, gas, and dust, should be sufficient to explain the gravity holding large structures together. It isn't. Not by a wide margin. Across the observable universe, the total gravitational effect measured through galaxy rotation, cluster dynamics. And gravitational lensing implies roughly 5 times more mass than all visible matter combined can account for, a proportion confirmed repeatedly by measurements of the cosmic microwave background from missions including the Planck satellite. The failure parade for this one is arguably the longest in physics. Massive compact halo objects, dim brown dwarfs, and rogue planets were searched for through microlensing surveys and found far too rare to close the gap. WIMPs, hypothetical weakly interacting massive particles, have been hunted for over 3 decades in underground detectors like Xenont in Italy, with exactly 0 confirmed detections. Axions, a lighter alternative candidate, remain equally elusive. Modified gravity theories attempt to sidestep the missing mass entirely, with mixed success. Nearly a century after Fritz Zwicky first proposed missing mass in galaxy clusters back in 1933, the dominant theory in cosmology rests on a substance nobody has ever isolated, weighed, or held. Roughly 85% of all the gravitating matter in your own galaxy might be made of something science still cannot name. We built a whole universe around something invisible. The next theory tries to erase it entirely. Number 4. Modified Newtonian dynamics. Israeli physicist Mordechai Milgram was working through the same missing mass puzzle Rubin's data had exposed. But instead of assuming hidden matter, he asked a quieter question. What if Newton's law of gravity itself simply breaks down at extremely low accelerations, the kind found only at a galaxy's outer edge, and nowhere in a laboratory? Standard Newtonian gravity assumes the force between two masses weakens strictly as the square of the distance between them. Everywhere. Always, without exception. Milgram proposed that below a threshold acceleration of about 1.2 times 10 to the negative 10 meters per second squared, gravity's fall-off changes shape entirely, growing effectively stronger relative to Newton's prediction. He published 3 consecutive papers in the Astrophysical Journal in 1983 after being rejected by Nature and Astronomy and Astrophysics letters. Laying out MOND's core equation and showing it could reproduce flat galaxy rotation curves using only visible mass, no dark matter required. The failure parade cuts both directions here. MOND fits individual spiral galaxy rotation curves with startling, almost suspicious accuracy, correctly predicting the Tully-Fisher relation between a galaxy's luminosity and its rotation speed. But it struggles badly with galaxy clusters, still requiring some unseen mass even under Milgram's own modified equations. It offers no natural explanation for the cosmic microwave background's fine structure, which standard dark matter models predict with precision. 40 years later, MOND has never been folded into a fully relativistic theory that satisfies the broader physics community, leaving it stranded as an equation that works suspiciously well on one scale and fails on another. 2 competing pictures of the cosmos, dark matter and modified gravity, have coexisted for 4 decades without either one landing a knockout blow. One camp says there's more mass. The other says the math itself is wrong. Nobody has proven either side correct. Number 3. The undetected graviton. Physicists building the Standard Model in the 20th century were simply trying to complete a checklist. Every known fundamental force needed a force-carrying particle, and by the 1970s, 3 of the 4 had been found or firmly predicted. The photon carries electromagnetism. Gluons carry the strong force. The W and Z bosons, confirmed at CERN in 1983, carry the weak force. Basic quantum field theory demands that gravity, if it's a genuine quantum force like the others, should have its own carrier particle too, a massless spin-2 boson dubbed the graviton. Nobody has ever detected one. Not indirectly, not directly, not in any experiment ever conducted. The reason lies in the numbers themselves. Gravity is roughly 10 to the 36th power times weaker than electromagnetism, which means a single graviton interacting with ordinary matter is, by calculations published across decades of quantum field theory literature, essentially undetectable with any technology currently conceivable. Physicist Freeman Dyson argued in a widely discussed 2004 analysis that a graviton detector sensitive enough to catch even one interaction would need to be so massive it would collapse into a black hole before it finished registering a signal. The failure parade includes every major detection strategy physics has ever devised. Particle colliders can't reach the energy scale required. Gravitational wave observatories like LIGO detect gravity's classical ripples, not its quantum particles. Cosmic microwave background surveys have placed upper limits on a graviton's possible mass, currently below 5 times 10 to the negative 32 electron volts, but a limit isn't a discovery. Every other force in nature has been traced down to its smallest carrier. Gravity, the one shaping your entire existence at every waking moment, might have a particle we are, by the physics of our own universe, structurally forbidden from ever seeing. We can calculate what carries gravity. We may never be able to catch it doing so. Number 2. The absence of a working quantum gravity theory. Physicists in the mid-20th century, flush with the success of quantum electrodynamics, attempted what seemed like the natural next step: apply the same successful mathematical machinery used to quantize the other forces to gravity itself. Quantum field theory had already tamed electromagnetism and the nuclear forces into predictive, testable frameworks. Gravity refused to cooperate. Every attempt to quantize Einstein's general relativity using standard techniques produced infinities that couldn't be cancelled out. A mathematical breakdown that never occurred with the other 3 forces. In 1967, Bryce DeWitt, building on earlier work by John Wheeler, formalized what's now called the Wheeler-DeWitt equation, an attempt to describe the entire universe's quantum wave function. It had a bizarre side effect: the equation contains no time variable at all. Applied literally, it describes a universe that does not evolve. Physicists call this the problem of time, and nobody has fully resolved it since. The failure parade spans generations. String theory proposed extra dimensions and vibrating fundamental strings as a fix, and after 50 years of development has produced no experimentally testable prediction. Loop quantum gravity proposed that space-time itself is made of discrete, quantized loops and remains similarly unconfirmed. Stephen Hawking spent much of his final decade searching for a resolution to related paradoxes at the black hole event horizon, publishing multiple papers on the subject, none of which achieved consensus before his death in 2018. 2 of the most successful theories in the history of science, quantum mechanics and general relativity, both confirmed to extraordinary precision independently, simply refuse to merge into a single mathematical framework. At the smallest possible scale, inside a black hole, at the instant of the Big Bang, physics does not currently have an answer for what happens to your own body's underlying matter. A century of brilliant minds hasn't closed this gap. The final entry explains why gravity might be broken by design. Number 1. The hierarchy problem. Particle physicists finalizing the Standard Model in the late 20th century were simply trying to calculate the relative strength of nature's 4 fundamental forces, a bookkeeping exercise meant to confirm the theory's internal consistency. If gravity and electromagnetism both operate as long-range forces with massless carriers, standard theoretical expectations suggest their strengths. While different, shouldn't be separated by an absurd margin. Instead, physicists found gravity is approximately 10 to the 40th power times weaker than electromagnetism, a gap physicist Ethan Siegel has described as requiring you to write out 10 million just to see the scale of the disparity in full. Take two protons a single meter apart, the electromagnetic repulsion between them outmuscles their mutual gravitational attraction by that entire factor. It takes roughly 10 to the 56th power protons, clumped together under their combined gravity, to overcome electromagnetism and ignite as a star. The failure parade reads like a graveyard of ambitious theories. Supersymmetry, proposed in the 1970s, predicted partner particles for every known particle that would naturally stabilize this gap, and after decades of searching at the Large Hadron Collider, not one supersymmetric particle has ever been found. Extra-dimensional models, including Lisa Randall and Raman Sundram's 1999 warped geometry proposal, published in Physical Review Letters, suggested gravity leaks into hidden dimensions we can't perceive, diluting its apparent strength in our own. Still unconfirmed. The anthropic explanation, that gravity simply must be this weak or stars, planets, and life could never have formed in the first place, sidesteps the mechanism entirely rather than explaining it. Every atom in your body, every step you take, every object that has ever fallen to the ground is being governed by a force so inexplicably faint that physics still can't say why it isn't roughly a billion trillion times stronger. A universe in which nothing, including you, would exist to ask the question. 10 entries. 10 unresolved mismatches sitting inside the most rigorously tested framework human beings have ever built. The universe is not confused. Every equation here still works, still predicts, still gets satellites where they're going, and describes galaxies with extraordinary precision. It's the explanation underneath the equations that keeps failing again and again. At the hands of some of the sharpest minds our species has produced, gravity is the force you feel every second of your life, and it remains the one physics understands least. If you want to see more videos like this, click the video on screen now.